All right, kids, welcome to the Chapter 4 New and Improved Calculus Test Review. The review packet is multiple choice. There may be a few multiple choice on the actual test, but I won't put a whole lot of stock into it. The answer is not always going to be C. So we're starting off, a lot of Chapter 4 was how functions behave. How can we use the derivative to tell us how functions behave? And first section here is how do you determine an absolute maximum or minimum of a function? Okay, these are important points on a closed interval. Now that's kind of key, closed interval. Okay, now I'm going to actually skip down to number 2 to kind of show a picture. Here's an example of a closed interval. It ends at A and B, okay, and it is continuous. So where the question is where can the maximums and minimums happen? Okay. And that answer is oftentimes maximums and minimums happen at endpoints. Okay, so you always want to check out, I might go back up here. Okay, you want to check endpoints. When I say check, that means plug in the endpoint value, the x value, okay, into the original function. So, for example, if A is one of my endpoints and B is one of my endpoints, the very first thing you should do is plug A into the function, see what it gives you. Plug B into the original function, see what it gives you. Because those are possible places where maximums and minimums occur. Okay? What else, or where else are things of interest to us? Well, we can see any place where the slope of the tangent line is 0, okay, is also a place that you want to check out. That's called the critical point. So you want to check out, so I guess first thing you want to do is you want to find where the function has a derivative that equals 0. And then whatever those points are, you want to check those out in the original function. Okay? In the original function. So check out those. And then also check out points of non-differentiability, sharp corners, holes, stuff like that. Okay? So you check out where the first derivative is 0, you check out the endpoints, and you check out points of non-differentiability. Okay, so that's kind of a review. And if I think everything we just said there matches with D. Okay? Evaluate the function at the critical points. We just talked about critical points, what they are. And at the endpoints, choose the largest and smallest values of the function for the absolute maximum minimum. Okay, so 1 is D. Number 2, determine from the given graph whether the function has any absolute extreme values. Okay. Well, that just means, look at it. Is there a highest and is there a lowest point? Yeah. There clearly is a maximum. That would be an absolute maximum at C2. Okay. And there's clearly a minimum, an absolute minimum, okay, at B. And I think the one that says that is A. Okay. Of your multiple choice, it'd be A. Now, I do want to let you know, this dot is filled in, and this dot is filled in. If this dot had been open, there would have been no absolute maximum. Open dots do not give you absolute maximums or minimums. I said that wrong. It would not have been an absolute minimum. Open dots do not give you absolute maximums or minimums. This one was closed. I don't have an eraser, so there is one there. All right, so anyway, A said that. 2 is A. Number 3, sketch the graph on a continuous function, from -3 to 1 that satisfies the given properties. Zoom out a little bit here. Okay. Now this is one where probably having the multiple choice is really quite handy. Okay. But what I'm saying is you're going to want to be able to draw these things without having the choices. Okay. So what are the clues that they give us? They tell us that the first derivative is 0 at -2 and -1. That means when I go to draw my graph, I almost want to do it without looking at the ones they gave us. Maybe I can do this. When I go to draw my graph, I know that at -2, okay, and I know that at -1, okay, we have to have a place where the graph has a slope of a tangent line of 0. Okay, It has an absolute maximum at x equals 1. So at 1, I'll have a max. Okay, and it has an absolute minimum. Absolute minimum value. Hold on, where am I looking at? Has an absolute maximum at x equals, has an absolute minimum at x equals -3. Okay, has an absolute and absolute minimum. F has a local minimum at x equals -1. Local. Okay, so they gave us a lot of stuff. So I'm going to kind of work backward. If it has a local minimum at -1, okay, it has a local minimum at -1, and I don't really know up and down wise, but I do know it has a local minimum at -1. And it has an absolute minimum at -3. That means that at -3 I must be lower. And here's the other thing. Okay, so I have a kind of a local here and an absolute here. Okay. It has an absolute maximum up at 1. So I'm just kind of putting, I don't know exactly where they're at, but I'm putting some key points here. Now this is what I do know. The derivative is 0 at -2. So at -2, it must be flattening out. Okay, but it's not flattening out higher than that one. We don't have that. So at -2, it's flattening out. At -1, it's flattening out. Okay, so I feel like I have something like this happening, flattening out. Okay. Now, that's how I drew it. I don't know if the multiple choice has one that looks like that, but this would satisfy the thing. At -2, it's flat. At -1, it's flat. I hit my absolute maximum at 1, which is an endpoint. I hit my absolute minimum at -3, which is an endpoint. Those would be possibilities. Now, when I look at the graph, okay, that they have for you, this is what they have. Okay. It's not quite as obvious. I guess they're saying that this is a maximum, and then there's your minimum, and there's your absolute, but that's how I guess they work their way through it. Okay. To be honest with you, I'd prefer something like this, and this is why I don't give multiple choice much, where I can clearly see what they're doing. Like here, it's kind of hard to tell where stuff is because it's pretty flat through there. All right. Anyway, number 4. Use the function below to answer parts A and B. Find the critical points, and then it kind of works you through there. Select the, I don't even know what that question's asking, but I can do this, okay? So, what I'm going to do is I'm going to find the first derivative of this function. And sometimes you don't have to do this, but sometimes I think people see this 3 down here and think they have to do a quotient rule. Remember, this is just negative 1/3 x cubed plus 64x. So when you do the derivative of it, which is going to help us find critical points, okay, you get negative x squared, because you multiply the 3 down, so you get negative x squared plus 64. Okay? And if I want to know where the first derivative equals 0, I'll set that equal to 0. I'll add the x squared over, and so I get 64 equals x squared, and I square root it, and so I find out that 8 and -8 are critical points. Okay? 8 and -8 are critical points. So I guess if you're filling in the boxes, that's 8 and -8. Okay. B, use a graphing utility to determine whether each critical point corresponds with a local maximum or local minimum or neither. Select the correct choice below. A lot of you have graphing calculators. That's not going to be a question tomorrow. But I do expect you to tell me whether 8 and 8 are maximums or minimums. Okay. Now, how would you do that? Okay. Well, this is how you would do this. You have critical points at -8 and 8 for the first derivative. I'm going to plug in values on either side of these intervals, something smaller than -8, something in the middle, and something like that. And then I will know what the sign of the first derivative is doing, okay? So for example, when I plug in 0, okay, I get a positive, okay? 0 squared plus 64 is positive. When I plug in 10, okay, now you got to be careful here, because when you look at this, you square 10, you get 100. That makes it -100 plus, so that's negative, okay? And then I'm going to plug in -10. When I plug in -10, -10 squared is 100, but that makes it negative, okay? So what is this telling me? Well, this is the number line analysis of the first derivative. And that's telling me my slope of my tangent line goes from a negative, on the original function, goes from a negative to a positive. So that means at -8, there must be a minimum. And then at +8, the slope of my tangent line goes from a positive to a negative. Okay, that tells me I must have a maximum. So at -8, I have a minimum on the original function. And at +8, I have a maximum on the original function. Now, I don't even know. I guess you have the answer key too. But that's what I expect you to be able to do. I don't know what all this crap says. Okay? Number 5. It looks like it's the same type of problem. Okay? So you're giving a... Oh, the other thing I should have mentioned here, I should have been careful about, is our critical points of 8 and -8 fell within the restriction of -11 to 11. Okay, so sometimes you gotta be careful. Sometimes you might get a critical point that isn't in the interval that they want you to work on. All right, number 5. Here we go. Same thing. Find the critical points. There are no points, and I should have mentioned this up there. There are no points of non-differentiability. This is just a polynomial. If there had been, I should have included that with the critical points. So now I'm just going to find the derivative, okay, and then end up setting it equal to 0. Derivative is 6x squared plus 13x, okay, plus 6, and that's on the interval -2 to 2. Okay, on the interval -2 to 2. Now I'm going to set that equal to 0. Because why? Because, well, where the first derivative is 0, that's critical point. This is going to factor, I believe. If it would not have factored, you would have had to gone to the quadratic formula. I think it's 3x and 2x. And the only way, what do I got here? 3 and 2. I think it's this. Plus 3 here and plus 2 here. Okay, sorry. Now here's how I can check. First times first is 6x squared. I got plus 9x and plus 4x. That's plus 13x and 2. Yeah, that's how it factored. Okay. So then I know that my critical points are at -2/3, okay, and -3/2. So it's a real tight kind of window there. Find the critical points. Use the graphing algebra where each point corresponds to local minimum, maximum, or neither. Select the correct choice, and if necessary, fill in the answer box to complete your choice. Okay, so all I'm going to do is this, and I don't even know if I'm going to do it out here. I might. These numbers are going to be kind of goofy. So -2/3 and -3/2 are your critical points. Okay. Now, if I plug in representative numbers for each interval, for example, I'll plug in 0. That seems like a pretty easy one to plug in. When I say plug in, I'm plugging it into the first derivative. So if I plug 0 into the first derivative, out comes 6. So that's positive. If I plug -10, that's something big, it doesn't really matter, into the first derivative, that means I'm going to check out this over here. -10 squared is 100 times 6 is 600. -10 times 13 is -130 plus 6. So that turns out to be positive as well. If I plug in a number between -2/3 and -3/2, like -1 will be the one I plug in. -1 squared is 1 plus, or times 6 is 6, minus 13 is negative 7. Negative 7 plus 6 is negative 1. It turns out to be negative. Okay. But once again, a number line analysis on the first derivative tells you a lot. So this is what it tells me. The original function goes from a slope that's positive to negative. So at this place, there's a maximum. And from here, it goes from a negative to a positive. So at this place, when x is negative 2/3, there's a minimum on the original function. All right, number 6. Sketch a function that is continuous from negative infinity to positive infinity that has the following properties. Use a number line to summarize the information about the function. Okay. Now this would be a good point. In fact, maybe I think I am going to skip ahead. This would be a good point to this to remind you what all these things are. Okay. So I'm actually going to maybe do this quick and then come back to question number 6. But here's what you have to know. A big chunk of chapter 4 was this. If you take derivatives, like the first derivative and the second derivative of the original function, it tells you stuff about the original function. Okay? So wherever the first derivative is greater than 0 or positive, then the original function is increasing. Wherever the first derivative is negative, is less than 0, then the original function is decreasing. Now, what does the second derivative tell us about? Wherever the second derivative is positive, then the original function is concave up. And wherever the second derivative is less than 0, then the original function is concave down. Okay, that's a big chunk of what we've been doing. The other thing I probably should mention is the second wherever the second derivative equals 0, that's called an inflection point. That's the place where the original function graph changes from concave up to concave down, or vice versa. So this whole sheet right here is checking to see if you understand that. The reason I'm doing it now here is also problem 6 and 7 are very similar to that. So we'll just kind of look through here. 1A, and when you do this on the test, make sure you're looking, is it original function? Is it first derivative? Oh boy, these little marks were kind of hard to see. Or are they talking second derivative? Hopefully it'll be clear when I put it on the test. All right, so here we go. On this one, where's the original function equal 0? Well, I can see places, 3 places, D, G, and K. D, G, and K is where the original function equals 0. Now, I know some of you are going to read this, where the first derivative is greater than 0, but I would think of this, where is the original function increasing? Where is the original function increasing? So as I start to trace this, no, no, no. D, yep, it's increasing at D. No, 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 no. Yep, it's increasing at J, K, L. J, K, L. Now, this is the one that kind of matters. If you say that it's flattening out here, you wouldn't say it's increasing. Like if you say there's a horizontal tangent line there, but to me it kind of looked like it's still increasing. So I think I will say M. Okay, so D, J, K, L, M. If you would have said, oh, I thought that was a horizontal tangent line, you would not have included M. Okay, then we go to section C, or part C. Where is the original function increasing? Now, right away, I know that my choices are limited to these 4 or 5. Okay, and the second derivative is greater than 0. Now, what did that mean? Well, it means I'm concave up. It's holding water. Well, D is an inflection point, so D is not part of my answer. J, that is on a section that is concave up. So J is part of my answer for That's part C. Okay. K, nope, that appears to be a flexion point. L, no, because that's concave down. And M, that's an inflection point. Okay. I think the only one is J, where the function is increasing and you're concave up. Like I said, if I miss one of these guys, let me know. All right, we go to letter D. Where's the original function have a flat tangent line and we're concave down? Flat tangent line and concave down. A is a flat tangent line and it's on a concave down, so I'd say A. E's on a flat tangent line and it's concave down, I would say E. I's on a flat tangent line, but it's not concave down. I think that's the only one, A and E. All right, letter E of this one.